All right, welcome back. There is a question right up front.
So I tried to rerun the program again, just with the same parameters like dropout 0.3 and L2 0.01, because I had like incredibly low accuracy compared to those, but now I got like 99.42.
Yeah, it varies quite a lot. I will talk about that now, basically, but at the end it's going to be summarized a little bit, because it's taking about averages and so on, and we have different regularizers that kind of interact with each other. Alright, okay, but yeah, welcome to the outline audience as well, to the last lecture, lecture 6, which is again appointed to some other area really in deep learning. It's about sequence data. Just for you also to realize that deep learning is not only about images, because the last 2 days we spent now quite some time always looking at images, and you get the feeling also from the media, perhaps with the ImageNet hype on big data and so forth, that it's only about images, right? So, but interestingly enough, here and there, and also new elements in Keras that you can use in Tensorflow to work, for instance, with other types of data that we can look at. So this will be part of our lecture 6, so to speak. What we will talk about is largely the limitations of typical feed-forward networks, right? What we used so far was basically always, even in the kind of deep learning sense, forward, backward, past, update, right? Back propagation, and there was no really recurrent aspect in it. So we will look at some recurrent neural networks. Who has used recurrent neural networks before? Okay, just one. Okay, 2, right? So we look a little bit how that works. This would be a complete tutorial again, right? To say that prompt, to use LSTM. It is just for you a pointer that deep learning works for others. However, it captures the essence, what you can do with it, and there's interesting application examples that you already know, like character prediction or Google Translate. We will look at this, how that works roughly, which is nothing else than stacked LSTM cells on top, and kind of interesting encoder and decoder approach. So this is interesting how that is already very much adopted here in the different, let's say, industrial examples. Hence I have also again a video where this is basically shown. However, interesting enough, we have done also lots of things, and I would like to take the opportunity before you leave now on the weekend also to summarize a little bit what we have done, so that you get all the things in order through all the different lectures, and also will point to some of the problems we've done, which largely point also to this, right? It's still a search in the deep blue sea, right? Where to find the good parameters, especially because we have just 2 here. Think about, we have epochs to think about, the learning rate to think about, so multidimensional thing. It's not so obvious like the cross-validation as last time. So in the kind of wrap-up of all of this, I would like to also have a group agreement discussion with you, so clarify questions, why there is so much variability. So what's the point in doing this? What could be cures, like taking averages, what you usually do when you publish, and so on. So this is a kind of indicator of where we go with this, and we have already seen, we kind of filled that quite nicely, so we can discuss quite good around that, but also it's an open floor for you for questions, right? So if you're kind of shy, please go ahead, now's the time, when we basically go to the end here of the lecture with a summary, ask all the questions you have for the different parts. So we'll go again from lecture 1, in a sense, through all the different lectures, just to have a kind of point in how that all fits together, right? So in terms of the group assignment, I will come now back to this at the end, because now we really have, let's say, everything almost filled and the people are doing more and more runs. It works quite well, so no problem using GPUs. That's also a very good, let's say, conclusion of our tutorial. Right, so let us start now by thinking again what types of learning you can do in the field of deep learning. And we already had said, basically you can do, many hidden layers, but this is really a danger in terms of overfitting. So this is not necessarily something where you consider always big wins. You rather go more specialized, right? Here you would say that artificial neural network in a general fashion, just neurons, dense connected, then there's 4 hidden neurons, and we already see for our dataset the accuracy goes down. If you add now like 20, which would be more the deep learning one, then you see the accuracy would be exactly going more or less because you significantly overfit. So hence we have seen it makes sense to do deep learning perhaps in a more specialized way, which means you have specific types of layers, not just neurons. They are all in the specialized fashion, and you learned the CNN already, in the specialized fashion also based on neurons inside, right? But they are arranged in a specific fashion, and the connectivity between the different layers are also in a specific way, right? The weight sharing we discussed, feature maps we discussed, it's not how a typical neural network works, right? So there's a key difference between these fellows here, which tend to overfit, and convolutional neural networks that we have seen have inherent regularization already, right? If you think about, we're doing now lots of regularization here, but we yesterday got already 84%, right? So maybe we have to think about other manipulation aspects that we can steer in order to make that better, or we have to do longer efforts and so on. So lots of parameters still to find out, but in a way we get already good results. If you remember also we compared it to the support vector machines, which are stuck at 77%. Part number one. Part number two, we used significantly time for feature engineering to go to 77%. You know, as a tutorial, people have just used the raw data. We did not any do feature engineering. Right? In a way, you bypass the SVM with all this manual feature engineering, just automatically learned in this tutorial a better accuracy. So this is the two takeaway message why the specialized layers here in the convolutional neural network really make sense. And apart from things like transfer learning that we just learned, that it could be even complete different area, these are interesting results. There are deep belief networks which are a bit more theoretical, and it's a very nice idea of connecting the different layers, but this would take another time. And it's not so obvious like the recurrent neural networks, which are perhaps a bit more loose than these ones. That's why I would like to put them here in the tutorial. Of course, it's also interesting to study, and there are more of them, like restricted Boltzmann machines you can study. So deep learning is a very rich field. Right? What we just did in this tutorial was scratching the surface. If you go to more advanced models, you can do the stacking, stacked autoencoders. There's a really big field to study, and lots of things are not really understood yet how it works in several of these domains. So it's a kind of very new technology to all of us, right? All in the machine learning field. It's something which we really need to know better in the next 10 to 20 years. And of course, take away the message when I talk about this really requires much more usually in order to use it properly and to understand it perhaps perfectly. I just want to make the point that this isn't Keras, right? So what I teach now, you can directly use it again with the tools that we have here installed in parallel, and it's basically also in the backend in Tensorflow implemented the LSTM cells. So that's why it's also very nice, and it's kind of intuitive for what they are used. Basically, it's mostly temporal behavior that you have in sequences, words, for instance, like that. As one example, it could be also time series of some signal from a mechanical, from some industry, whatever your measurement device is, interesting. Right, so for all of them, maybe this is a key consideration. They all don't really work well if you have not really enough data, right? But we said before, transfer learning then could help here and there in order to apply. So, exactly, so that would be a first exercise I usually do. So when you have a artificial neural network, right, we just discussed today, and yesterday we have forward, backward pass, right, update weights. How you would encode now a series of words in order to predict the next character. Let's say I have hello and would predict world. That's usually a computer science example. How you would do that? Yeah, there's an idea.
What you could do, for example, for the phrase prediction is introduce half phrases and try to make it predict the last one. Like, you give as training the first half of the phrase, and labels the second half of the phrase, and then for the next one.
Right, but then you need really labeled data saying this and this will be always W afterwards, and you do lots of manual things for this label. But in the moment, you can learn from some Cobra, right? But it's like, in a way, we miss the connection to the things that were before, right? Especially if you think about the next character. If you just hell, for instance, heil, and you want to predict the hello from hello world.
Maybe you can reuse the previous information with the new information in order to get.
Right, that's an idea. You kind of need some storage, some memory, where you put the previous information. Right, this already points to exactly the limitation that we see in artificial neural networks. We can do it either manually and prepare the data very well, but let's look at this a little bit elaborately. The key problem that neural networks in the feed-forward have, and this is now a distinction to the recurrent ones, is exactly this, that we do backpropagation, right? You have learned that already with the chain rule, taking derivatives and so on. Here we compute the signal, and the way back we update the weights. That is one pass through the network, and we do it again, batches, always independently, and we have no idea here what's happened before in a sense. There was some sample pushed through, right, depending on the batch and epoch we are in, partly randomly picked, and it will update then the net. So how should I know what's happening before? Right? If I now put, for instance, a signal of an H through it, how should I predict here an E for hello, right? That this is the next character. So we see that a little bit, the typical application examples when you, for instance, have the next word in a sentence, or Chinese language, as I said, I think yesterday already as a small example. You have lots of European words throwing through that, but you need just one Chinese character plotting out, right? It's usually like this, they translate to this. Chinese is very, let's say, compact, and the signs are very rich in the features. I think we have perhaps some in the audience even that can confirm that. But how you do that? And this is the kind of limitation that you have in the typical feed forward, right? You just have one pass back and forwards, one sample through, learned, batches through, learned, but we have no idea what's happening before, what X's were there before. And this is exactly now where recurrent neural networks start to basically attack this problem of having a recurrent connection. So in a way, you preserve a little bit of memory what's happening before. It's the general idea of how you could visualize this is, for instance, this. You would give your signal through it in some specific time. Right? So now we come to the idea of time series, of sequence data. So there's always an index that you take it. Is it a time step, or is it a kind of specific idea that you have in terms of a kind of large measurement somewhere for some device, long time series? You still would have always a specific point in time that you can put in the network, and given through this recurrent connection, you can do this now again and again and put this through. And the interesting thing is we'll not lose necessarily all the information. Of course, most of the information will do the weight update, as we have seen, and will basically generate the network, will learn from the network, but some things we can preserve in some, let's say, in this recurrent connection. For instance, if you put here 1, you just say it always firing and brings you back, of preserving some of the information. If we put this a little bit bigger, because we're going to extend that to a specific purpose in LSTM cells, this is usually the TANCH, which you have here in kind of this implementation, which is nothing else than an activation function we already know. Right? We use a rectified linear unit, for instance, in one of the models in the convolutional neural network. What it does is basically here it has values between -1 and 1. That's an interesting property for us later when we look at the LSTM cells. However, it passes from one iteration through this and has a kind of short-term data dependency. Now this is a little bit a problem as well. So it works actually already quite good for some of the sequence data. So I'm not going to say that RNNs in general are problematic, but for short-term memories only. So hence, if you have a whole big book, and you would say, for instance, you read about France, right? This book would say, blah, 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 I've been in France, and then a couple of sentences further, I tell, and this guy speaks French. This connection will be lost also by a recurrent neural network. It cannot capture that. It's too long, too much short-term memory, which is then dropped in terms of favor of more recent aspects. So we need a way to preserve a signal across all the different time steps. And this is exactly where the LSTM starts to work. And this is a kind of the problem where you say, we have memory, hence the name short-term memory is inherent in the RNN model. That's why we pass the signal again and can preserve some of the information, but not on the long term. Hence I will talk now about a long-term short memory. It's a bit misleading name, but that's where it stands for. In order to capture the essence of this memory cell that we're really going to explore now, we can unroll these recurrent neural networks. It's nothing fancy. It's just saying that instead of putting the signal again and again in our network, what we always do also with feed-forward networks, we do the same with recurrent neural networks. We unloop that or unroll that over time. Right? Everybody can see that this is equal. Right? It's x0, x1, xt. Right? And there's a problem of vanishing gradient and lots of theoretical consideration which we normally would go into, where the problem now lies that we cannot really have long memory in these models and so on. This is something which we need for a complete lecture, right? So it is a problem in the sense of preserving here the information. And here's a kind of, let's say, backpropagation through time approach. There's even a, let's say, modification to this backpropagation algorithm that we know. You would consider that because basically the forward and backward paths are now a little bit more elaborate to think about. Yeah, that's why we say it's backpropagation through time. Still, the idea of minimizing an error function is still there, right? That you have basically the backpropagation forward and the backward updates. But it's a backpropagation through time algorithm, which is a little bit a modification for these recurrent structures. So the interesting thing is, if you, let's say, zoom into that, the RNN model is, in a sense, if you take just the typical RNN model, everything we know about a neuron, right? So a neuron takes a signal and fires an activation function. That's what we already learned, basically in the normal hidden layers, in the neural networks basics yesterday. So it's kind of limited. Now you're wondering why there's so much space probably inside that, because we're going to extend it for the specific purpose of putting memory into it. And here it's usually where it starts, where we have to go a little bit more elaborate, right? So what you see here basically is the signal still goes in and enters a so-called LSTM cell, right? And this is one of the building blocks you can actually use in Keras, in Tensorflow. It's implemented, and you can steer that to your needs. However, you see here the sigmoids, and you know the sigmoid function is quite well explained and very helpful for us because it basically crunch everything between 0 and 1. So you can use them in a sense as a gate, right? Of saying I leave something in, or I kind of block it. It's kind of a binary helper function. Or I maybe have here the touch still firing the signal, so that's unmodified. But I have here some modification to some form of memory, and I can influence this memory in a nonlinear fission, which is this operation, when I want to put something in memory. Hence, when you now look at these complicated setup, think about that this is a key thing which enables us now to remember, right? Just this kind of through time aspect. These is all just help us to forget, because sometimes it's even maybe very useful to forget things in the memory, right? We want to null it for some purpose. Next page in the book, next chapter in the book, whatever. It depends on the application it has. Then we want to have an input gate. Of course, new information flowing in, but we want to preserve, right? Like lots of text, maybe in a static fashion. Many of these will somehow memorize. We talked about France. Very important, apparently, to say and predict this guy speaks French. There's a direct connection in time somewhere, and actually that's where it's used for instance, right? For this kind of aspect, predicting these new words. Of course, it will be more elaborate. You don't have then one cell. You think about now, this is one cell over time, right? xt minus 1, xt plus 1. Right? So these are the different signals per time still going in. Right? So it's always the next character or whatever it is in terms of problems. Here you steer like, okay, is it a forgetting? Do I have to renew it? Will I take it out or not? Is another question. And then you just use that for the next iterative time step. And through iterative learning, again and again, as we know from backpropagation, we always can have our memory signal inside. Now, the aspects for the questions that I had at the beginning was, yeah, I have to memorize, but then I have to do it manually. The interesting thing is, if there's a repeated signal very strong, and the recurrent neural network will kind of try to do that themselves and learn how to do this interesting behavior here, to put something in the memory. So it's a very interesting aspect if you think about that this is, again, an automated process, right? Hence the name, long, short-term memory, right? So again, looking back, the short-term is something we already had with the recurrent neural network. That's not new to LSTM cells. But with this modification that you have through these different cells in that perspective, and if you now stack them up and use multiple of them, we will come to this point, then you have several multiple memories which preserve more longer. This is a term, long short-term memory, hence the name. And it works extraordinarily well for everything which is sequence data, everything where you have a time step in the data. So if you have a scientific problem in this area, don't go to the convolutional neural networks, which are for images. Consider LSTM cells and stacking them up. Right? So this is something which is a quite interesting field as well to study, but mostly not for image data, much more for time series and so on. Hence, this is a conclusion. Right? So you have kind of a cell state that always influence the next time step, something you can keep, can modify, depending on the strength of the signals, throwing through these gates that are basically here. Or reuse it then in your nonlinear function that you have anyway for the neuron. And this is an interesting aspect, and it's just there for you to try out in Keras. And it could have lots of different modifications. You will see, when you see it in Keras, you can a little bit steer how that cell look like in general. Right? But in the way this captures the essence, you have a memory across a time. Now an application example that makes it probably very clear. You still have the probabilities that going out of that, so that not yet is a kind of 100%, this will be the next character. Right? Again, think of it as a classification problem that we had in the softmax from the convolutional or from the artificial neural network at the end. What we get out was not a clear class. We got a probability that this class is better than the other one. Right? Some between 0 and 1 probability, and we take the strongest one, of course, of saying this is then probably this particular class. In this sense, you have the same thing which goes in the time series. So for instance, here's this typical word, or in this particular example, even character prediction. Right? The hello world, when we are stuck at the hello, this is what we get in, and we want to know what would be the next in time. So what this thing we're giving out, and this is basically then the LSTM cell that you see here. Instead of a typical RNN model, I put now this all in this gray box, right? Consider it not as just a tanh, but the whole gates that we have for this cell state. And what you enroll then is nothing else than having this, what we just discussed. But the interesting thing is it can be used then to predict the next, let's say, character, as in this example. So if you go in H, this needs to be encoded, could be different ways how you encode it. Could be words that come in to predict the next words. But don't take these characters only as one explication example, but you get it in, and this is a prediction for the next time step. And it keeps, let's say, the history of this time series a little bit in this memory cells. And this makes it so effective to talk about this model. Right, so again, if you're interested in time series analysis, I have one PhD that is finishing next week in time series. Now we have very interesting results with LSTM cells compared to very old traditional models in time series analysis. Right, just because LSTM cells are extremely effective in finding aspects. Could be anything. We do water mixing events detection, for instance, in 2 fjords with traditional time series, and there are lots of techniques actually. It's whole courses that you can have in Iceland and everywhere just for time series analysis. Anyway, so that's the next way to study. Again, I cannot go into all the details, but if you're seriously interested, you have everything at hand now. You know about regularization, validation, this will be still a key concern when you do that. but they have layers that you just know how to add. You know, model, add, LSTM. And then, of course, you're a little bit here confronted with a little bit, kind of a bunch of different configuration options, but if you look to them in the API, you will see some of them you basically can ignore or can just try to play around with your time series. And this is an interesting property. It's all there for you. It will be then using the GPUs or CPUs underneath of TensorFlow. It's here installed, so you can already take it, basically look at it. And it's quite nice. Also, if you may be interested in another leak, because now we're leaving the space of the tutorial, also Theano has a support for it, or you can create it, and this is a very low level, but maybe some of you would be interested in using it because it's very similar to NumPy. So anyone who's using NumPy, it's very, you see, but there are all of the people that raise their hands, right? And if you are there, the step to Theano is very, very short. It's maybe another interesting deep learning framework to study. Right, but here's also an example how you then do it with basically these interesting things. In the end, it's all sigmoids tanh influencing the signal, so there's no new math introduced. It's just the way how you arrange it. And the interesting thing is to have this property then, of course, in a stacked fashion. We come to the stacked fashion in a moment, and of course here and there are references. If you want, if you want to look at this and work in this field, perhaps look here and there at the kind of references. TensorFlow itself has it also, but as you know from this tutorial, you don't really face it. However, what we don't previously discuss is that you can also mix, because it's Python. There's no point in having a problem of saying suddenly from Keras, you use some of the TensorFlow aspects, right? You can still do that, but in this particular example, you could use a Keras LSTM, and it will automatically use the ones from TensorFlow, right? But if you're interested, you can of course combine as you like. It's a beautiful aspect to do. Here and there, maybe for some of the application problems, but they have also a basic LSTM cell that you can use, and if you look at it, use it quite bluntly, very quickly, because it's here installed already in parallel, so you could have quite some big time series to analyze. However, this is just the building block in terms of Lego. You would say it's the smallest entity you can have. Now in Lego, we're not interested very much in having just one little block, right? So usually how it is, you stack them, you bring them together, right? Similar like we did in transfer learning, of saying one convolutional neural network just does feature learning, and afterwards I do another convolution for my classification. We stacked up this kind of behavior. We can now think about for what can I use these LSTM cells together, right? To stack them up, to use more and more of these Lego cells. And this is an example that probably the most of you already know, right? And it also explores why it's not so simple as we think. In a way, it works like that. It is Google Translate. Who has used Google Translate? Right. How it works actually for Chinese characters? Do we have some people that have experience with that? Maybe for Chinese characters, it works well. Yeah.
Not really.
You see, right? It works well even for, admittedly for me as European, very heavy, very hard material to study. One sign has lots of meanings where you put it and so on. It's really interesting. If you have just 1 hour just to look at it, it's really fascinating, this language. But when you think about now, you have to translate that. It's amazing. So you need again a time series. It doesn't matter if it's to Chinese or from Chinese. So here's an example where you have Chinese letters, and then you want to know what it is exactly, what would be the next here in translated text. Right, so this is one example where you use now the LSTM cell that we just discussed. It's just a, let's say, kind of version here, which is simplified. It's not looking like that, right? Again, it's one LSTM cell. We come later to the idea how really the network works. But the simplified, you could say, you have the different signs coming in. And for the next sign, I want to predict, this is coming in. I have here some in-between kind of, we would say, transformation into another model. And this, what we would call here a sequence-to-sequence model, means you just have two recurrent neural networks. Right? They're for different purposes. Because translated text also predicts the next. Right? If you think about, first we have to translate, which is a little bit here the kind of through vector that is between. And then we want to predict what is next in this sense of the prediction that just came out, which is very likely from that, just as translation. So this is nothing else than, in a way, doing the typical next word, next character prediction, but now, of course, we have a different meaning and need some learning of some history, what would be here the next to fire. Right? So this is a kind of simplified way of saying this is the encoder in the original language, and we need now to decode what's coming up. Yes, what's up? And right? So I don't know if the Chinese actually, do they match with that? I always wanted to ask that. Someone who is actually reading that, can you see, is it true that yes, what's up would be possible next follow-ups on these Chinese signs? It's an interesting way. So this is an example coming direct from Google, so we can go back and ask that, right? It's really true. No, but I think with Google Translate, I use it several times with Icelandic and it works pretty well. And it's actually a very nice tool. However, if it would be only so simple, we don't need LSTM cells or recurrent neural networks at all, right? Which you see a little bit here, which I cannot talk about very much. It would be now leaving really the tutorial space. But you have still your time series, you know, that basically has then here some intermediate, and the encoder, all of these, is a really stacked up version of this kind of LSTM cells. You see here a little bit maybe on the other side, it is 8 layers, and they are distributed across several many GPUs to compute all of that, right? So this is not a simple thing like it looks here, or like I put here just using one LSTM cell. It's a little bit like you have a memory, and now you have to put it in place in the network, what you want to store, where you want to store, and how you arrange it, right? And this is of course something to remember when you see things like that. There's just a little bit here, a couple of LSTM cells. Usually it is unrolled, where you say the time series is clear, but of course a parallelization and all of the mapping of a stacked LSTM really, right? Every cell here captures now a memory aspect of your time series, and could be different things, right? Especially if you think about European, peng, fire, one Chinese sign. Right, this is something which is one example of this, or the other way around, with the Chinese signs now expressing firing up several of these cells to fire up and to use their memory. It's a little bit a really interesting field to study, but you see how elaborate it is, right? Just for you as a feeling, it is deep in the sense that you have now much more layers of this recurrent property. With this, you have much more memory capacity to actually store information from the time series you have before. And then typically, as I said, also you have them for different purposes, right? So this is an encoder kind of thing in terms of this side, and then you have another recurrent complete, in a sense, independent, just connected with a kind of thought or attention space here, and then basically have in the end, kind of the kind of big structure again for learning all of that, what I need on this particular side of the language. But here you see, in the end, it doesn't change much of the softmax, it's still a probability to fire. Right, and you now bring that in perspective of the convolutional network that we learned already. It gives you out some probability at the end, okay, it's this word, that word, or this, basically. And if you would actually give that out, or what you see in Google Translate is then the one that has the highest probability. That's why sometimes it's misleading, but in many cases it has very high probability. Now, this is one of the examples I want to show. Perhaps we can go in between the group assignment, but I think the running on the GPUs goes very well. In that sense, you maybe just want to get some more numbers if we have them. Otherwise, we don't mind so much. Is this group perhaps? We're waiting for that quite some time. Is there some news?
Our parameter dropout is 0.3.
0.3?
And
this one, probably.
Yes.
How much?
75.
75%. Okay, thank you very much. Any other? Yeah?
The fourth row and the third column.
The third column. Like this one, yeah.
Yeah.
Very obvious, right?
The overall accuracy is 81.2%.
Okay, well. 81%. Excellent. We have just 3 missing. Basically these and these. Is anyone? Yeah, you have a value for that one? Yeah. 35. Okay, interesting. Yeah. And the rest of the fields? Yeah, in the back?
The bottom left,
This one. Yeah.
23.8.
23.8. Excellent. Thank you very much. Now one just missing. And then we have done our work and can go to the weekend. Otherwise we stay here Saturday, Sunday just to compute that. Without reservation we have no GPUs, so we use CPUs and it will take longer. Now what the team that is doing that? I don't know who was that? Yeah.
Still running.
It's still running?
Yes, that's straight. Already 3 hours.
Okay. Well, maybe Kenneth, could you have a small... But thanks for the feedback, that's why I wanted to have this small interrupt. We will discuss it at the end. Let's have a short idea where all these kind of LSTMs could be useful. It's a little bit longer movie, but I think it still captures the essence that there's much more that I cannot teach in all this short time. The LSTM is just the beginning. You have a gated recurrent unit, which is also often used today. So the building blocks of this Lego, if you want, if you compare it to Lego worlds, are different, right? Depending on your application problem, and you can combine them in an interesting way. So it's another field of deep learning which is very rich in to be explored for you. So let's have a look while we solve this issue with the GPU and go into the summary of today.
What do you do if the patterns in your data change with time? In that case, your best bet is to use a recurrent neural network. This deep learning model has a simple structure with a built-in feedback loop, allowing it to act as a forecasting engine. Let's take a closer look. Recurrent neural networks, or RNNs, have a long history, but their recent popularity is mostly due to the works of Jürgen, Subho Riedel, and Alex Graves. Their applications are extremely versatile, ranging from speech recognition to driverless cars. All the nets we've seen up to this point have been feed-forward neural networks. In a feed-forward neural network, signals flow in only one direction from input to output, one layer at a time. In a recurrent net, the output of a layer is added to the next input and fed back into the same layer, which is typically the only layer in the entire network. You can think of this process as a passage through time. Shown here are 4 such time steps. At t equals 1, the net takes the output of time t equals 0 and sends it back into the net along with the next input. The net repeats this for t equals 2, t equals 3, and so on. Unlike feed-forward nets, a recurrent net can receive a sequence of values as input, and it can also produce a sequence of values as output. The ability to operate with sequences opens up these nets to a wide variety of applications. Here are a few examples. When the input is singular and the output is a sequence, a potential application is image captioning. A sequence of inputs with a single output can be used for document classification. When both the input and output are sequences, these nets can classify videos frame by frame. If a time delay is introduced, the net can statistically forecast the demand in supply chain planning. Have you ever used an RNN for one of these applications? If so, please comment and share your experiences. Like we've seen with previous deep learning models, by stacking RNNs on top of each other, you can form a net capable of more complex output than a single RNN working alone. Typically, an RNN is an extremely difficult net to train. Since these nets use backpropagation, we once again run into the problem of the vanishing gradient. Unfortunately, the vanishing gradient is exponentially worse for an RNN. The reason for this is that each time step is the equivalent of an entire layer in a feed-forward network. So training an RNN for 100 time steps is like training a 100-layer feed-forward net. This leads to exponentially small gradients and a decay of information through time. There are several ways to address this problem, the most popular of which is gating. Gating is a technique that helps the net decide when to forget the current input and when to remember it for future time steps. The most popular gating types today are GRU and LSTM. Besides gating, there are also a few other techniques like gradient clipping, steeper gates, and better optimizers. When it comes to training a recurrent net, GPUs are an obvious choice over an ordinary CPU. This was validated by a research team at Indico, which uses these nets on text processing tasks like sentiment analysis and helpfulness extraction. The team found that GPUs were able to train the nets 250 times faster. That's the difference between 1 day of training and over 8 months. So, under what circumstances would you use a recurrent net over a feed-forward net? We know that a feed-forward net outputs one value, which in many cases was a class or a prediction. A recurrent net is suited for time series data, where an output can be the next value in a sequence or the next several values. So the answer depends on whether the application calls for classification, regression, or forecasting. In the next video, we'll take a look at a family of deep learning models known as the autoencoders.
Right. Okay. So I think that's really pointed a lot of other areas as well, which I didn't touch, like the gated recurrent units, interesting to study. You would have autoencoders, stacked autoencoders, and all the message of stacking really the simple cells together. We have seen in Google Translate, of course, you can use for many different applications. Before we go to the summaries, there may be a question related to LSTMs, time series analysis, sequence data. No question? Yeah, please.
Can you use this kind of networks or LSTMs also for, well, updating your weights when running your network? It's maybe difficult, but when you have something like that, running your network and your data is shifting a little bit, sometimes you could completely misclassification that your network is also updated.
I'm not sure I completely understand the question, to be honest. Yeah. What is your typical network? Is a LSTM?
Is CNN, but sometimes.
CNN. Okay.
Yes.
Yeah. So not time series.
Yeah, but sometimes yes, I'm in between. Sometimes time series, but my ECG this time can something shift just a little bit because of electrodes sweating, and then just a little shift in my ECGs, and then it's completely misclassification. So that you can use this kind of LSTMs or just to update.
Well, for this type of data, LSTM would be interesting to study, definitely. They would probably memorize some of the properties from previous runs, if you even specifically stack them, so different properties of how the time series evolved. And from that we'll see that some of them, you don't fire. You would say, okay, that's a kind of going away from the normal signal or kind of going towards noise and outliers, if I understand it kind of correctly. So I think everything which has really a sequenced nature can be done. So, but what you basically get out is a forecaster, not really a classification aspect, right? This is the second part of your question, so how you could do that. However, you could do that maybe as a feature encoder, but you have the same time series looked at, and you mark these in the time series of saying being difficult processes to either remove them as outliers, or you basically take them and use them as additional feature maybe to your classifier. But it's generally, I think, a topic which needs more discussion, really, to go into that. Because it's not that simple of just throwing an LSTM cell on it. You really have to look on that specifically. All right.
Boris,
Any more questions?
the answer is there for the last ones.
Very good, very good. After 3 hours.
No, it actually finished an hour ago, but the job is still going for some reason,
okay.
but it's actually done.
Wow, I thought so. Friday evening, probably want to go home at some point in time. Okay, we are listening.
84.
84%. Okay, excellent. Thank you very much. That's pretty much here. Like 84%. Yeah, interesting. Thank you very much. All right, now we have an interesting discussion following about this. Before I go there and open the floor for all the questions, I would like to go a little bit through what we learned, right? Step by step in the summary. And don't hesitate to ask here and there, because we have now a small review of all the tutorial again, just highlighting here and there some important things about our classification, convolutional networks, our application domain, and so forth. Right? To just memorize what you basically learn in your brain before we go home. So the first things we started from was basically we had this perceptrons, if you remember, and we add hidden oops, yeah, again, thank you very much for the microphone here. Right, so the first thing we started was basically adding hidden layers, and because of the exercises here and there, we get disconnected with the material. Also, one reason I wanted to do the summary, that you have one flow, right? We always interrupted to get the exercises. Normally in the university or in a good course, you also have the kind of more getting things together, right? Here it was very interactively, which is good for the practicals, but here and there you maybe lost the connection. That's why I just bring it again as a summary. When you think like, we started with a perceptron, that's clearly not a model that could cope with this data. Still, it managed quite well because the data itself, when you think about it again, was more or less simple in the sense that it was a toy data set. Right? A simple model worked here because it's a simple data set, so to speak. Right? Immediately, if you would take this and put it to remote sensing data, then you would have issues. But you see, really, the kind of accuracy that we had in this field was always just a couple of percent. Right? We worked ourselves up. Right? We started basically with 95 or so with the perceptron, added 2 layers, have been at 97, added the dropout, have been at 98, and then came to the convolutional neural network at 99. So we kind of more improved ourselves yesterday. Over the time and today, basically always increasing a little bit on this accuracy. So this is interesting. So think about this now in the deep learning things is dangerous. Of saying just adding more hidden layers and adding more regularization will all solve my problem. We see already in the variability of these, they're dangerous in that fashion. So it's not that simple in deep learning. You have done this with having, kind of this 4 layers, for instance. And if you increase that, you would perhaps try at home 10 layers, you will see that the accuracy already goes down. That was part of the summary. We learned then the kind of convolutional neural network model that is very beautifully implemented here in Keras. It's a very quick prototyping that you can use. And we have seen it is also in practice, of course, relevant what you kind of do in terms of how you create this architecture. Right? And if you now think about, we talked just in the last lecture about how beautiful it is to have all the features automatically learned. Don't forget, there's still some time that we invest of creating all of this to your specific application problem. Now we also learned that we have Overfeed, we have AlexNet as a good blueprint, a recipe, so to speak, for some of our problems. So it's a good way to start, but really the fine-tuning is usually that where it costs. And the fine-tuning lies in between these things we just have here, between 82, sometimes 75. Maybe I just have to do another epoch run with other 5 epochs, 50 epochs added. Maybe I have to change and come back to my architecture and see, with all the regularization in the world, it's still not really working out. So a mistake in the architecture could also happen. So you go backwards, basically, not only fine-tuning, so do rough new architecture development. It's really something like, as you've done before, as a machine learner, you would not consider perhaps a problem and say that's a problem for neural networks. It's maybe also very good in classification to use random forests. It might be interesting to use support vector machines. You use different models to tackle practical problems, right? You're not stuck in one particular problem. Hence, you remember the Iceland had several approaches that the people did in the last lecture. So there are kind of 10, 12 different versions of the Iceland. And this is, of course, now my practical way for you as a summary. And you will spend a lot of time doing this. Also, if you win the time of feature learning, right? This is all feature engineering and so on, and you have now feature learning, that's nice. And don't underestimate if you promise to get something out of convolutional neural networks, at least take a buffer of 1 month from practical experience. Right? Don't go to your boss tomorrow, I have a very big, good data problem solved with convolutional neural network because I have been in this course. Right? It's not that simple. Just taking the MNIST architecture that we have and throw it now on some other character recognition also doesn't mean that it will work well. Right? It depends, is it intensity, is it RGB, maybe it's a colorful kind of photo, text, is it, historical text, for instance, with what we had once in one application Iceland, with Viking characters and so on. You have lots of interesting application examples where you think, well, that should be just learned as well as MNIST, but take away the message that this is, of course, relevant. You have already nevertheless learned what are the building blocks, and you see, in a way, it's magic, what all the people say, now deep learning is magic learning features, but under the hood you learn it's not magic. You know how to create it. Convolutions, the nice property, doing downsampling, max poolings, the different poolings, of course, average pooling and so on. And doing this in a stacked fashion, right? This number, or this kind of idea of stacking, we have learned that now in LSTMs with recurrent neural networks, or here in the different convolutions. It doesn't say you should stop here with 2 convolutions, maybe 3 solve your problem. You do another layer. Different models, solve the problem. So what I'm essentially saying is, maybe if you come, and have settled the model, then you go to the fine-tuning, like here for instance, and you see, okay, there's lots of variability, switch back, and maybe, okay, either I can simplify my model, that would be always better. Like Occam's razor. It's a typical machine learning philosophy saying simplest model better. We have also learned it in one of the videos that we've seen about overfitting. Right? Maybe it is better to remove a convolutional layer and we can have much more neurons or much more feature nets in one. It's something you have to here and there try out. If you see lots of problems, perhaps in your data, when you use it in kind of fine-tuning aspects. Just one example. Going further, we have the output of the model, 99%, and this is really unusual in practice. But it's just because this is really a digestible problem. We have lots of samples. If you think for just a small problem, 28 by 28 pixel, and it's a whole scene, it's not a pixel-wise classification. And then we have 60,000 samples, right, already labeled that we use. So in this sense, you can already see that it's quite nice to come that high, but in practice a warning. So when you go now to your bosses or somewhere in industry, don't say I can do everything on this level, right? So usually what we see in practice, we are never about 80%, rarely, or 90% would be already good when it comes to very complex models, right? So this is, going towards 90 degrees and higher is really something where either our overfitting rings the bell, so that is something where we have to be very careful about, or we basically have an error in the model or the data sets. So be careful what you promise. That's my message here when you think about having done this course, and we have done some image recognition on the 99% level. However, if you think about that there were some characters we didn't recognize, if you don't go the machine learning way, it's still worth maybe trying in your domain, right? Even if you don't get towards 99%, as you will hopefully see, machine learning is an interesting way to start tackling this problem. If you have lots of image data, try things out. The convolutional might be interesting to catch some of the properties and patterns as we have seen. Another takeaway message, deep learning is really for GPUs, right? Who disagrees with me on that? Okay, good, then the learning experience is there. We use CPUs here and there, we use GPUs. By now you get the feeling, right? What kind of order of magnitudes of time gains is it? The interesting thing is just the convolutional neural networks, LSTMs in the same way, they do always the same thing, more or less, like matrix multiplication. We had it in one of the lecture, the updates of the weights, Wx plus b, in a sense, that we learned at the beginning, right? It's always updates of weights coming out of some nonlinear function and so on. And this is beautiful parallelizable as we learned. Hence beautiful for the GPU. What you also learned is getting them is not so easy. We have just 5 for the tutorial, otherwise we could have one, maybe the full model that I leave for you as homework. Right? Remember, we significantly downsampled our problem here. Right? We have 58 classes normally. We had 16 classes only. Right? So if you're at home and would play around, you can use the other data set, the full site, the full blown one. And also, my recommendation would be use GPUs for it. I mean, you can use the CPUs, but you will see it will take extremely long to train them and so on. So hence, deep learning and GPUs in a way go together, mostly. So Tensorflow is very slow and all other models are usually very slow on all the CPUs. Then, here the example, think about problems which are normally nicely parallelizable, and this is what we had already in matrix multiplications, matrix vector multiplications. All of this, of course, works very nicely, as we discussed. As a summary, I would like also to send a little bit that we got the time and make you aware how difficult it is sometimes to get GPUs. And we should be thankful to Leuven in this sense. Even if there are problems, it's just usual. If you are in the distributed computing domain, HPC domain, there are always errors sometimes. Right? It could be the scheduler has some problem. There's a problem with the file system. You can access your data. As a machine learner then, it's hard to start if you don't access your data. It's just normal that technology will fail, and even TensorFlow and Keras, if you take the pain of compiling it, I think Kenneth can tell you something about it. It is intensive in technology, so we have to live with that. Still, it's nice that we got the GPUs because we could have good things done. However, you also have seen how quickly, hopefully, this pace is. Right? We have now one gentleman at home that has one at home, which is a bit more advanced already, much more faster. We had some old ones here, the K20s compared to the K40s, which are perhaps not very much years old, but already showing an order of significance lower in performance. And you can expect now what's coming up from NVIDIA, the new generation of cards, and this will be a continuous game that you also play. And on top of that, we have, from experience, usually the problem, the software packages are usually following the cutting edge. Which means if you have very old CPUs, it gets harder and harder for you to use the frameworks with that models, right? Hence, it's something we didn't discuss so much. Clouds could be an answer for you if you, for instance, don't have access anymore at the university. You go to business, to industry, and want to create your own startup, or basically join a company. For instance, Amazon and other cloud providers have also GPUs you can, let's say, rent. And based on that, of course, you can have, the technology pace and run with them. That's the positive side. The negative side is usually you have good people here in the center, like Kenneth and many others, that you can call and say, I have a problem with compiling this, and that doesn't work. At Amazon, you have a general support staff that doesn't help you with your scientific problem in question. You just rent. You swipe a credit card, you get the kind of metal in terms of GPUs. There's no one that you can say, well, I have a problem with this particular setup. More and more cloud platforms come. The Google platform is, for instance, one example. Is another interesting space which already provides more and more high-level services in that area. Right? Still, it's a pace which is enormous, and it's something to observe for you just for the practical experience now, kind of a summary. These are the things that perhaps here and there get lost between, switching again, switch exercises and theory. So then we got more sophisticated. We have seen the 2D convolutions. We just were actually discussing 1D convolutions. You can do that as well, actually, in the break. But you can also go more sophisticated, the 3D convolutions that we have seen, which is also interesting now to think that you have a 3D neuron setup, right? If you compare it now to the neural network that you had otherwise, which we always see here at the end, normally, it's just, let's say, a flattened version of that. But still think about the order of magnitudes of computing that has to go through that 3D aspect. Right? We're talking here about much more neurons and much more computing of this kind of matrix multiplication. And exactly there is where the GPU again counts, right? It's these errors flowing through. Here is where the computing is done in order of magnitudes of these weights updates. In the end, still, we have learned that going from the traditional modes we know, here the output with, you know, fully connected layers and everything, is not so much of a difference. You still, you know, forward the signal and learn from the backward process when updating the weights. But we have much more flexibility today. For instance, now the majority of people will start with the ReLU, with the rectified linear units. 10 years ago, no one would think about that. It's another example. There are lots of optimizations we didn't discuss because we don't have time, like batch normalization, right? And this would be something where you can significantly reduce the number of epochs. And there are lots of different techniques, which means you normalize basically after each of these layers and so forth, which we didn't discuss. Adding more and more to the complexity that I would like to demonstrate with this, and later on with another slide, that you have so many things to work on that this is, of course, an active research project. Nevertheless, saying we have already 84%, right, which is already very good compared to the traditional classifier of 77%, this doesn't mean that this is the end, right? We're still researching how to better that and to make that better. You know, better ideas of truth, maybe having more of the normalization. What are the right parameters to put in terms of regularization? What are the right methods for the optimizer? As you remember, today no one would go for SGD necessarily, unless you could put the momentum as an MS drop in, or you put the ANN in. You have different optimizers. So, you know, just a simple normal SGD is like, okay, that is still people doing outside in the field, but it's not cutting edge. Meaning there's so much pace in this community that it's hard to, let's say, work on all of them at once to improve your modeling. But step by step, you probably can go and increase your modeling better and better. Right, that is mostly what I wanted to say about this architecture. Again, remember, we did on a very small scale this kind of thing. That's why the computing was so fast for your GPUs. It's another aspect of learning the turnaround time of that. Right? If you want to have a real problem now tackled, for us here with 58 classes, you do changes, you have to compute. Changes, compute, and to see, do they really matter? If you have a toy problem like the ANN-MNIST, that is no big deal. But if you have, of course, an application problem, this costs GPU time, and you usually get that just through peer review in science, or basically if you go to Amazon, you have to swipe your credit card. So it costs to do these modifications, which is another issue. Why not can you do, you know, all the modifications, the grid search, in the sense we did here with all the parameters, and just, you know, get the best out. Usually it's not possible because you don't have access to it. And the second one is the turnaround time. If you remember, this 58 classes take, like, depending on which GPU you have, a full day, for instance, just to compute, or in a more advanced, maybe like a couple of hours. So it's something to consider also. It's not like typical compilation, software engineering aspects like programming C, Java in an interactive fashion. You have a remote, it's a batch submission. Sometimes you get scheduled as well as you have realized, right? We had here one good example, waiting, that could happen to you as well. You're waiting for GPUs, they're used by someone else. Another turnaround time issue. Not only takes it long to train, also the GPUs are very attractive these days, so actually to get hold of them, like we had here in the tutorial, as it was a very nice thing to have. Right, then we can, you know, look on the small data. This is just an example. Think about, again, this is probably something a lot what we can do now in terms of bettering our model. And has someone an idea why? When you think about the small data that we had used. You see, the kind of architecture we did was optimized for 58 classes. And now we have something with 16 classes. We use the same architecture for this smaller problem. Right? With this, we also could consider now changing the architecture again and modify that here and there perhaps to capture, you know, we have now a big model complexity necessarily for 58 classes, but probably can shrink that down to get, let's say, higher accuracy and so forth. Right? I think the one that we have on the normal architecture is like 84 here and there. You see, we can capture that, right, in some of the runs, definitively, but still you can also tune on these models. And the full data, you see, basically we are kind of here, so if you have any idea how to improve that and you are working with it, and now at home and at your GPUs at home, don't keep that for yourself if you have 95%. We would be very interested to listen if you get better accuracy, for instance, right? Because as you know, this is in the moment the cutting edge that we got. Like at Jülich, like 84, something like this. And also using regularization apparently doesn't help so much, lots of variations in it. So what are the next steps? So we could do longer learning, increasing the epochs, right? Or perhaps using not anymore SGD with NMNIST, but use rather ANN or another optimizer. So you have now all these kind of things you can work on in order to better the model. And if you have, let's say, 90%, we would be very happy, basically, if you report that to us. Maybe we can also learn from each other, because as I said, there's no big, good recipe now to say we can definitively improve in this way. There are so many options of freedom where we can now try to better the model that it's really hard to go to. Right? I hope that is very clear. The space, the hyperparameter space is really huge. Takeaway message also was a transfer learning, right? I think I discussed now in the break with many of them that are going to try it maybe. It's really an interesting aspect if you consider it. Again, you have a big data domain somewhere like ImageNet, all is pre-trained for you already here and there. At the final layers, or not the final layers, as you read the message as a copy-paste error, I think, then where you kind of partly use here what's in this kind of features learned, right? And then you can, look really to unseen data, do very good things, even if you have rare ground truths and so on, as we discussed in transfer learning. Right? Something which will be also probably much more common the next 10 years, that this will be not something very new in a sense. And transfer learning itself has been there before, but we have like two movements which I didn't discuss before. Firstly, many people put their data much more open than in previous times. Right? And with this, we have, of course, the opportunity to access data we never had before. In the scientific community, for instance, we are more and more actually encouraged and required to open our data. If you publish, in the future, the publishers will request that you put your data open. Right? Because we have many papers in the past that are based on peer review, but still have no results in an open fashion, so it's hard to reproduce the results. Right? In this sense, it's an interesting movement helping us in the big data domain, deep learning domain, to learn better. And this is, of course, one aspect of the story. Secondly, we can consider that the computing power with the GPUs will increase, and will be just helping us of doing much more quicker cycles of this modeling. With this, you have much more ideas of how you can tune the model. You're not stuck now with a full course, a whole day, just checking two regularizers. Right? So in a way, we just took all our time today just to fill this little parameter space. Again, think about, we have another dimension here with a learning rate. Maybe if you take like this, it's a third dimension, then it's another parameter. Now we have to do all of that again with a different learning rate. Now we do all again with a different epoch idea and different optimizer. So you come to the point again, this is hard. Still, the interesting thing with transfer learning, that's what I wanted to say, there are some recipes around, especially in image recognition, right? That you can maybe take like LSTM, Google, different ones, overfeed we discussed. It worked already very well for some of the problems. Take advantage of that before you create completely your own ones. Right, overfitting is something which I also would like to brand in your mind, right? As I said before, this is a key problem we have in machine learning, and we have the two cures that are very important for you to also think about. So always when you read a document or someone is presenting to you some good achievements in terms of accuracy, the first question you ask, what validation steps do you have? What are your regularizers? If someone comes to you with 85% accuracy, you doubt that first, right? That what we usually do as reviewers of jobs, we reject everything which doesn't talk about regularizers or validation steps. That's a key thing in machine learning, otherwise you automatically overfit in most of the cases. Hence, for you, always something interesting to study. Admittedly, it's getting more complicated as convolutional networks, artificial neural networks in general are very parameter intensive. Right? We have a more simpler way of doing this with support vector machines and maybe also random forests and ensemble methods in that sense. Hence, still for you very important alarm bells. High levels of accuracy, for instance, is usually something you have to doubt or talk about at least what would be the regularization. Hence here and there the theory of regularization, statistical learning theory, how many samples do you use for your problem? Right? This is another thing you basically should see when someone is talking with you with a machine learning model and says high accuracy, okay, how many samples did you have? The same way as you start. So this is a very important consideration. Right, then we have seen actually, for instance, here the regularizers are there, and that is just some of them. There's, again, other ones we discussed here was weight decay, for instance, L2, there's L1, and then you can consider that each of the different areas have perhaps also other ideas. Interesting enough, the most packages have this, but it's often neglected, right? So the people just don't use it necessarily, and which is of course quite strange, because in a way we have seen how simple it was to use a regularizer in your problem, right? Now what you usually have, a little bit alluding now to our practicals, is that when you report something to your bosses, take averages usually, right? What you did not do in the SVM lecture as well, normally what you do, you take averages over 10 runs before you report anything. And this will largely capture here and there that you get like 10% or 5% differences. However, this is another issue with this particular modeling, that we have so many other areas where we could tweak and tune our model that perhaps this is not the right way to do it, right? Also, if we think about that, maybe things we did neutralize, again, when we think about that we penalize here, for instance, very large weights. Right? This is what the weight decay is largely doing. So if you say you penalize especially those which are very large, then you basically say, okay, the 50% of them you kind of neutralize again, which means this regularizer outperforms this one. Right? Because here, every weight has to suffer from this. It's a weight decay. You penalize all the weights, especially the large ones, the strong signals. And with this kind of one, you say 50% of them that you just penalized and so doesn't play a role. And on top of that, which explains here and there where you have 5% differences, or sometimes even 10 if you're unlucky, means think about dropout as a whole. It's a random process, ignoring by each backward forward, the cards are newly stacked, right? So who is now the one that is winning? You basically go here and say sometimes a strong signal is kind of basically blocked, and sometimes it passes through. The strong signal are important for your features, right? For your accuracy in the end. But with this, you're also saying, well, half of them will be ignored. But with this other regularizer, you kind of counter engage in this problem. However, for a more reliable estimate in that sense, what you would do is you take the average 10 times. And what I think here and there we could also improve of thinking, because we penalize so much here and there, right? In the extreme values, we need more epochs to train. Some of the things probably will, over longer time, if you use 2,000 epochs, I think now we have like 1,000 or something, that here and there we penalize the model so much. Think about what that means. That means the effectiveness of one epoch is 50% only. There's a dropout here, right? Because you don't use a signal randomly. And this is 50% of your weight. So 50% of your learning progress is removed. So the 1,000 epochs are not the 1,000 epochs you did, in a sense, without this regularizer. And now you see that how that all fits together, right? You need, for instance, here now a third dimension of saying you perhaps more have to increase the epochs here and there. However, we will see trends. It will be not jumping extremely here and there in terms of the field. So we see a little bit like here a trend with this capturing of the two, and here basically in this area having a relatively good one. Right? But if you report these numbers, taking into account there's lots of random aspects that are part in the batches. There are random aspects that you have in the dropouts significantly at each of the different forward backward passes. Some individuals shows. If you average out, it is unlikely that a strong signal that contributes to this high accuracy will remain to be always penalized. So this is something over the averages, like 10 times firms doing that will help. Now the practical problem we have, we know that it's sometimes infeasible to do, right? So we think now, if we have to do this once, it's already a day for a complete class. Now if we do this now 10 times and average out of it, you get the story, it takes much more time. However, in a way, you just automate the process again. You schedule it, and at some point in time over the weekend, where perhaps some of the scientists are not so active, they will probably then, sometimes scheduling the job, and then you have the results. Right? Again, showing you how long basically this process is to work on these problems. Right. So there's a question.
If you train the kids, is it really necessary that you always start training from the beginning, or should it be possible to reuse the weights of a previous grid cell?
What was that again?
So, for example, if you take the top left cell, what we now did was if we change the combination, we retrained the network from 0 on. Now the question is, could we reuse the weights of a previous cell to train the next cell? Because that, of course, would decrease the training time every time. Because then you don't start with random weights, but you start with the weights of a previous cell.
Yeah, good point. I think something like this you're alluding to is going through the grid search in a systematic way, right? Of saying you learned from these weights and then do that.
So you instead of really training from the beginning on, you start with those weights, and then, for example, if you increase the dropouts, then your network will see that and it will adjust the weights to adjust, for example, for overfitting. But yeah, it doesn't have to train the network always from the beginning on. So in that way, it's similar to the
transfer learning.
You reuse somewhat what you already learned, and that's maybe can decrease the total time of the grid search.
Right. I think that's a good idea to do. Here and there, of course, we have to be careful of saying what we're doing in terms of the weight decay. So it doesn't help if you say I have spent 1,000 epochs here and I just do 50 then here.
Yeah, of course, you really need to train enough again, but you can maybe do something like retrain until it stabilizes again or something.
Yes, in a way you could do that, yes. I mean, that's possible, and actually something what I didn't talk about so much, we do checkpointing every 10 epochs of storing the data. That is what you see and have already also in the callbacks. Right? If you look in the scripts that are provided to you, there's a callback script, and what we do in practice just for checkpointing is every 10 times they're storing it. And you potentially just load that up and use a different model. That's right, but think about you use a different model, alarm bells, right? Learning, overfitting, learning from something which not the machine learned. You learned as a human here and said, okay. And you don't do it on a validation set proper with the learning. So here's also, again, a little bit optimistic bias then, right, to go into this direction. You're kind of doing a decision on a model which is not by the machine. Careful about this, but in general you could do that, but also take into account it will be not fitting just with a couple of epochs. You need then also the whole learning process again, especially if you think about this as a drastic one, 50% of the learning is removed. From 1,000 epochs, effectively 500 I use. 500 are too little to make really a clear adjustment in terms of accuracy. You need more time to learn, to get a bit more, let's say, stable signals. And it will turn out. However, you don't have to do 10,000, then maybe you go to another direction of optimizing. But what a good question. In a way, it captures the essence of transfer learning, if you want, right? You just send a different signal through. Here, you use the same signal, would be even better. But in transfer learning, you're doing the same thing. In the sense, you store the model as that, and then put kind of you start from the learning already pre-learned, pre-trained. Right. But in general, as I said, advanced topics for you to study in that direction would be things like particle swarm optimization. This is not a new problem. Artificial neural networks, in a sense, suffer from the same problem of having too many options, right? In SVMs, it's, as I said earlier, kernel parameter, cost, and so on. It's a relatively space in terms of parameter, which is easy. Neural networks and more elaborate models have lots of parameters, and this kind of genetic, inspired algorithms, they search their way through the good parameters in a semi-automatic fashion. So there are studies, of course, which are advanced topics of helping you with all of this, right? To get to more useful kind of parameter combinations. However, no one gives you a clear recipe of saying this or that is now to be done, right, in the sense of saying. Right, another question maybe related to the grid search before we go and discuss more about the summary. Anytime, just ask me something and we can discuss, right? It's a discussion session now. We have some time. There's no snow outside, or is there? The sun is long, yeah? Okay. Right, so this captures the essence of our discussion, right? When we see now maybe training epochs, and I put a lot of regularizing, like decay in it, and or dropout, which are significantly more bad, especially their random dropouts in Keras, right? So that means 50% is removed. Or I use another optimizer here, say SGD is quite often, I use ANN for it. And there are even more, there's ANN-MNIST prop, for instance, sometimes works pretty well in some of the applications, but it's something you cannot know exactly, you have to put it to your application problem. Here and there, again, you have your blueprints from AlexNet, but it's a, let's say, typical image recognition problem, but many in science have some difficult problems, like we heard in the tropical area, which is not so easy to have the labeled samples, so you have to go much more unsupervised. There's not a really directing recipe for that. So the problems that are outside are not necessarily dog, cat, cow classification that Google is doing effectively with these models. We are, in science and engineering, often faced with problems which are much more deeper, right? Like pixel-wise classification, remote sensing, we have seen, and so forth. Hence, these are all configuration options plus the regularization values that we have seen now here, and it is really a complexity which requires lots of computing time to be tackled. And with this, of course, technology enhancement in terms of when you think about what we have right now here in Jülich, that was helping already a lot, but of course, it's already outdated in a year, then we would probably laugh about what we have there in Jülich and would go already to the next step. If you think about supercomputing, they announced Aurora. It's an interesting supercomputer to think about more from GPU's perspective, right? They don't compete in the sense of the typical simulation sciences, it's just a GPU cluster from NVIDIA, and it's very interesting to see. Okay. Right. No questions from your side? The group assignment, everything around LSTMs maybe, I left that a bit out. Of course, this requires a bit more study. That's also very interesting in terms of results. Okay, let's have another movie then to encourage you to get active again. It's Friday afternoon, so we want to be having something from the afternoon. Just maybe a short summary that I found about some interesting applications we didn't talk that much about, but where deep learning is also interested. I think in some with the people I actually discussed in the break, because then you are more active in talking with me. So then we talked about games. Right? I think that is a very interesting part. Reinforcement learning that we had in the past, now powered with deep architectures, something we didn't play and looked at. And we will see some of them in the videos, but there are interesting results in that as well. How they optimize themselves to get the best scores automatically. Right? We didn't train them from basically doing like given always the same sets and learn from multiple of them. They learn features, how to win games. Right, not steps, like a typical computer would do like 10 years ago and would say we already have a good memory as a computer. It's very simple for us to predict the next one because we have computing. It's more about how you learn, basically, how to win the game. And one example is usually always the one that has a kind of playing ping pong, right? Not against another one, for instance, just against some scores that you have usually on the top, and you can, just have a ping pong, and he optimizes the nets in the case of really using the most per each of the kind of pawns you have for this game to get the most scores out. So it uses significantly, let's say, the right and left to get to interesting patterns we would never thought of as humans or cannot do because we're not the accuracy in terms of getting the ping in that way that the pawn will get all the different, let's say, points out. So again, it's an interesting subject to study for you who is perhaps interested more into gamings and this part. One example will be here in the video. And there are lots of things we didn't discuss in deep learning, just the surface. An interesting future to study.
Dear fellow scholars, this is 2-minute papers with Karol Zsolnai-Fehér. There are so many applications of deep learning, I was really excited to put together a short but really cool list of some of the more recent results for you fellow scholars to enjoy. Machine learning provides us an incredible set of tools. If you have a difficult problem at hand, you don't need to handcraft an algorithm for it. It finds out by itself what is important about the problem and tries to solve it on its own. In many problem domains, they perform better than human experts. What's more, some of these algorithms find out things that you could earn a PhD with 10 years ago. Here goes the first stunning application. Toxicity detection for different chemical structures by means of deep learning. It is so efficient that it could find toxic properties that previously required decades of work by humans who are experts of their field. Next one, mitosis detection from large images. Mitosis means that cell nuclei are undergoing different transformations that are quite harmful and quite difficult to detect. The best techniques out there are using convolutional neural networks and are outperforming professional radiologists at their own task. Unbelievable. Kaggle is a company that is dedicated to connecting companies with large datasets and data scientists who write algorithms to extract insight from all this data. If you take only a brief look, you see an incredibly large swath of applications for learning algorithms. Almost all of these were believed to be only for humans, very smart humans. And learning algorithms, again, emerged triumphant on many of these. For instance, they had a great competition where learning algorithms would read a website and find out whether paid content is disguised there as real content. Next up on the list, hallucination or sequence generation. It looks at different video games, tries to learn how they work, and generates new footage out of thin air by using a recurrent neural network. Really amazing. Because of the imperfection of the 3D scanning procedures, many 3D scan furnitures are too noisy to be used as is. However, there are techniques to look at these really noisy models and try to figure out how they should look by learning the symmetries and other properties of real furniture. These algorithms can also do an excellent job at predicting how different fluids behave in time and are therefore expected to be super useful in physical simulation in the following years. And on the list of highly sophisticated scientific topics, there is this application that can find out what makes a good selfie and how good your photos are, if you really want to know the truth. Here's another application where a computer algorithm that we call deep Q learning plays Pong against itself and eventually achieves expertise. The machines are also grading student essays. At first, one would think that this cannot possibly be a good idea. And as it turns out, their judgment is more consistent with the reference grades than any of the teachers who were tested. This could be an awesome tool for saving a lot of time and assisting the teachers to help their students learn. This kind of blows my mind. It would be great to take a look at an actual dataset if it is public and the issued grades. So if any of you fellow scholars have seen it somewhere, please let me know in the comment section. And these results are only from the last few years, and it's really just scratching the surface. There are literally hundreds of more applications we haven't even talked about. We are living extremely exciting times indeed. I am eager to see and perhaps be a small part of this progress. There are tons of reading and viewing materials in the description box.
All right, okay, 4:15. We're a little bit early already with everything, unless any one of you has questions. We have time. Even for the philosophical ones, yesterday we had the robots neural nets, creating neural nets, where it's getting dangerous. Yeah, please, sorry.
Yeah, still one question for our regulation. You mean that we can rerun the configuration to have stable results, maybe repeat 10 times for each configuration? But my question is that how do you say 10 times is sufficient or not? Maybe we need 20 times, 30 times?
Very good question, yeah. So this alludes a little bit like rule of thumb, right? And from published previously here and there, the matter of average is an important thing. So you will see perhaps still maybe here and there it will be too much varying, but then I would be alarmed when it perhaps with 10 average would be like that. Then you rather increase the epochs. Because I think, in a sense, when you think about the learning process, which we significantly in some of the areas blocked, right? And the epochs is your learning, if you remember, right, in time. Then you rather take another way of tuning the model. You not say just averaging everything will help, right? So this 10 was just out of experience, and also experts will accept that, of saying, if you average these runs 10 times, right, you get a relative beta estimate. That has something to do even with statistics, the expected value of experiments. The more parameters you have, of course, the more I would doubt that average then, you know. It's something also you have to make key for consideration and then go to another optimization, like increasing epochs learning rate, something we also not discussed very much, right? Just in the beginning, stochastic gradient descent in itself has problems of local minima and so on. So things we didn't discuss, if you just change the local, the learning rate, you maybe bypass the kind of local minima where you in the moment are stuck. There's another process which is not a physical formula, right? It's an error function we go downhill and we don't know how it's really shaped. In this sense, it could be also some of these aspects which you basically improve instead of doing the average, is first of saying, let's play around with the learning rate. And then you have now this momentum term, the new ones with Adam and so on, the velocity, not only acceleration, also velocity of more tuning parameters in that. So optimization procedures in itself. You have different cost functions to think about, right? And cross entropy and so on we discussed. All of these could play to the game. Yes, yeah, welcome. Thank you for the question. Yeah, there's one. A question about gaming now.
No, actually not. It's
no,
about,
okay.
It's about one of the earlier lessons about convolutional neural networks. So the idea is that, for example, Google is doing image classification on all kinds.
Can you speak up a lot? I'm so sorry. I don't hear it very well here.
So Google is doing this image classification on many everyday objects like desks and chairs and things. But to make this practical, it needs to work on different resolutions and sizes of images, I would say, and then how you use your network, because your network has an input layer with a fixed size as far as you see.
Right. So your question is how it generalizes to other images and so on.
Different resolutions.
Right. Well, this is encapsulated basically in the features that you learn when they detected somewhere in some way. Right? They're location independent. It could be somewhere on a big picture, let's say 2000 pixels. If the feature is there, and you go with this direction, you basically do a crop of that image and put it through that, then you detect it. What you usually do, you go down in the resolution, right? So you cannot take 2000 by 2000 pixels now and put it through the network. That would be, having, exploding all the computation capacity. So what you will do is basically you normalize and you go back to the size where you trained your network on. I think that is kind of your question, right? And with this, you have information loss, right? It's actually a nice follow-on discussion of saying, if you would have more computing, if you could now put the whole big, every times the real resolutions from human brain cuts, so they have extremely high pixel resolutions inside that, and then convolution by convolution work on that, we would be, on a very good situation. However, we just do patches where we have labels from, which is another problem because, if you have big resolutions of pixels, which means creating ground truths, means also more work on the pixels, right? Second kind of problem, especially if you're pixel-wise. But if you have the Google problem, that's a, let's say, much more simpler aspect of doing so. right? With identifying cat and these kind of things, because of the scene-wise kind of classification. That was a good question, yeah.
I have a follow-up question as well.
Yeah, louder, please. Thank you.
Yeah,
I should also repeat it maybe for the streaming, I guess. Sorry.
So I have a follow-up question. Say you have two photos of the same resolution. Both contain, for example, the dog, but in one photo the dog covers the entire picture, and in another photo the dog is like in the lower right corner. So how can your kernels that learn your features work on both of these images? Because okay, it's location independent, but now you have a different scale. So your features for your dog that fills the whole frame are larger than those for the dog that is in the bottom right corner of the frame.
Mm-hmm. Yeah, it's a good question. In some cases this will even fail, I would say, but here and there would even have some things which are the features that are recognized. And you would see that, for instance, ears, eyes, and so on. You learn that over lots of averages. Right? It's not you take one dog and see how it is like there in this kind of little, let's say, image. Right? The situations you just discussed is basically, from practicality, not happening. Because you not learn from one dog that is capturing the whole image in order to classify it. That would be machine learning not possible. That would be public Cheremenko saying number of samples not good enough. What you would have is 100,000 dogs you look at. Now, if they happen to be all, let's say, big and being on the complete pixels, that could be the case that you don't really learn a small poppy capturing on 20 or 10 pixels somewhere in the corner. Or you misclassify even often, would say that's a tiger. Because the amount of pixels, you typically would then crop or downscale your image so much that the identity of the dog will be lost. Hence, it's more a data pattern question in a sense. It's not a problem for the network per se, but you will not come to this in practice. That would be my assumption. Because you have 1,000 dogs, and the chances are that they are different sizes and so on. And from that, the signals will learn the dog a little bit, not in this particular case. I think I just have a direct kind of translation, a little bit how it looks like, right? We had this kind of in the beginning of this lecture even. When you think about how they learn, and hence you need big data for it, right? It's again not 2, 3 kind of, I think it's in the other lecture 5, I guess, where we had this discussion around, the different layers when you look into that. Which is actually also nice, just comment in the discussion maybe for you. There are tools in TensorFlow which allows you to explore the layers. So my initial idea was also do more visualization here, but last week I encountered this HDF5 view that it's not a good way to do in a tutorial. Right? We have your VLAN and it's not really useful. And it was so slow, you're looking at a point cloud alone, and HDF5 view is there, however, installed. For instance, when you now want to look on the remote sensing datasets, you can do that. Just basically load the slides from the last tutorial. There's a small explanation how you look at HDF5, that you can look at the data. Right? Equally, TensorFlow has a tensor board that we didn't discuss. So there's lots of tool sets around for visualization, some of the features. However, coming back shortly to this, how we learn here, shows a little bit also how differently you would basically detect that it is an elephant. Let's pick this one, right? It's your dog somewhere. So the practicality is that having, them here, having thousand pictures from practice, they always, turn around and so on. And this is what the network will learn based on the features. So I think it's a kind of practical domain question that the case you just mentioned will not happening, or I would say even there's no machine learning because you have just one case. That is a very interesting question, yeah. Thank you. We have time?
Would it mean, for example, that in the first layers, a small dog in a picture would guess? Would go through different features in a large dog? Because in the first layers...
Well, the first layer has nothing to do with the dog. That would be directly the blunt answer. The first layers usually have very little. And this is not the first layer. That's maybe a bit misleading. Right now, when you think about what we learned with convolution, also a good question. You're not here at the first layer. This is already a well-developed feature map. What I left out is what you can see in the publication. There are edges, as I said, like edges, corners, in order to detect something. So that's what we probably would say, like the corner here. That is how we actually recognize a table in our first visual cortex. Then we go further and say, there's some structure around, some plate, next two layers in the visual cortex, more digested. And now we get the feature, okay, it has kind of, this is how the first layers are, so that you basically have no connection to the dog in a sense. It contributes to the dog in a higher hierarchy. Like, let's say, consider a leg. Yeah, there are legs, maybe in a kind of elephant, but also in a kind of giraffe. The basic properties in the beginning of the layers will be the same, and they share that feature. You know, you go up and up in the hierarchy through the different convolutions we discussed. They contribute to each other in the signal strength, and only in the higher level you will basically form the signal strength that this will be an elephant, while the other way was going the giraffe. And the way how you steer that is over time, then of course with error propagation back. In many cases in that learning, it will be probably the case that at the beginning they share the path, and then a giraffe will end up here. And they will say, oh, it's very similar, high, not so high in an elephant, but you know, it has like kind of this interesting path through the network, and then your back propagation will say, no, it's not an elephant. So then we'll learn from that, the signal will be reduced, while in the giraffe, where it will ending, will be strengthened. And over time, you will do this in the higher layers in terms of your dog, or in terms of the giraffe or elephant. At the beginning of layers, there is no concept in that. The beginning of the layers is really just rudimentary aspects. Hence, it's also something to think about transfer learning, right? Where you want to cut your feature space and so on. Maybe it doesn't make sense to have completely the latest layers here used. Maybe it's also sometimes used for saving, you know, or having better accuracy, just having some of the layers reused that are more general. That's kind of what I'm saying. Right? General features, and they form up in a hierarchical fashion to really precise layers.